Today we're gonna be talking about understanding antimicrobial resistance. Now, in simple terms, imagine you have a drug that works on an organism, meaning that the drug is going to stop the growth of this organism, and it just happens that this organism can provide illness, and we don't want that. So all of a sudden, this drug does not work. And the reason why it doesn't work is because of drug resistance, which is present in the organisms. Now, for this, I like to talk about natural selection. Now, we all have DNA, which is our blueprint, right? Also, organisms such as bacteria, viruses, fungi use this DNA to spread their own existence, right? Now, when you have something, a characteristic that is visible and is unique and provides an advantage, this is what scientists call uh, phenotypic variation, right? It's what you can observe that makes it unique, makes it different. Now, all of these results that all of these lead to that the organisms have more descendants, more babies, which are born in comparison to those that can actually survive in the environment. How they survive is different. Now, if there is a drug resistance, it basically means the drug doesn't work. By looking at the bacteria, for example, we know that bacteria can become resistant by changes at the DNA label or by the transfer of the blueprint. The blueprint is DNA. Bacteria have this mechanism called horizontal gene transfer, which basically means that either they pick up cloning DNA in the environment or they just transfer little pieces of DNA that are in a circular form to others in the process of spreading this. Or transduction is when you have phages, right, that are involved in viruses, and that's how you can transfer DNA. In terms of prokaryotes, and prokaryotes are bacteria, you must consider to be able to understand evolutionary fitness for bacteria, you have to understand how they survive, how they reproduce, and the transmission of this. These are important concepts. Now, relative fitness gives this picture, and this is sort of a comparison by counting how many babies an organism provides in compared to the other, and you get a ratio. This is relative fitness. So it allows us to understand how they differ to one another. Now, there is something called fitness cost. And having a change at DNA level can be great because all of a sudden the drug doesn't work, doesn't affect the organism. However, such change can have deleterious effect on the normal functioning of the affected component. And when I'm talking about component, I'm referring to how these drugs affect the component in the organism, how this happens. This component could be a protein. Protein is made of amino acids, or an enzyme, which is basically a protein. However, it speeds up reactions, and these reactions can be very crucial in the normal functioning of the organism. Now, the emergence and spread is affected by this phenotype. Now, this phenotype is antimicrobial resistance. How does it come about and how it can spread? This is, in simple terms, when we have fast mutations which happen, this means that we can promote these changes at the DNA level, and as a result, we have the advantage in the organism. Also, if you have a bigger genome, it just means that there is more chances that you have more mutations that can lead to this result, meaning that you have this adaptation mutation that allows the organism not to be affected by the drug. In conclusion, antimicrobial resistance, in essence, is natural selection, which is part of evolution. And now that's how this is a very basic concept that can allow us to dig deeper in more um, literature related to that antimicrobial resistance.